In our Galgotias University, we have advanced geotechnical and earth science laboratory, and the students were performing unconfined compressive strength test. You can see that the unconfined compressive strength test was explained to the students, and they were told about the confinement and unconfinement. So what is confined? If you are providing some external support or a cover to the specimen, that is said to be confinement. So here you can observe that the soil sample is not having any external boundary and it is left as it is as per the site conditions, and so there is no confinement. This test is called unconfined compressive strength test, and it was performed as per IS 2720 part 10 code book. Now you can see that the diameter of the specimen is 38 millimeters and the height of the specimen is 76 millimeters. And here we are going to measure the unconfined compressive strength, and based upon the unconfined compressive strength we can also determine the shear stress by using Coulomb's law. Now the students are here involved in recording the observations where the record says and displays the relation between load versus deflection or displacement, and the students were told about how the curve is varying. The curve was non-linear, and you can see that the peak was obtained at 4.8 kg loading, and the corresponding displacement was recorded as 2.7 millimeters. And here you can see that the axial stress is the only factor that could be defined by this experiment, because there is no lateral confinement, and this test is thus called unconfined compressive strength test. And the students were involved in recording the values of load versus displacement, and 15% the load value corresponding to 15% strain was said to be the peak load as observed from the graph. Now this equipment was used for performing the experiment on unconfined compression test of the soil, and clay sample was used for the test. And you can see that this apparatus has a proving ring, and this proving ring has a sensitivity of 0.01 kg, and you can also see the loading frame. The capacity was about 2 tons, the loading frame, and the test mold, as I told you earlier, is about 38 millimeters in diameter and 76 millimeter in height. Now you can do the test in two ways. One is undisturbed sample and the second one is molded. So this resembles the site condition, and you can compare the UCS test with standard penetration test also, so that the comparison will lead to some decision for using the particular site or accessing the particular site conditions. Now this was the failure pattern observed by the students. And basically this type of failure is adapted, and you can record the failure patterns. The students prepared a mold of dimension having diameter of about 38 millimeters, and the height of the sample was 76 millimeters. And here you can see that there is a ball that is being provided at the center, so that the load is applied uniformly and the alignment is at the centroid. And the response of the loading was recorded by strain dial gauge fixed, and load the readings were taken for every 5 mm of compression, and this equipment was attached to the computer, where it started displaying the original load versus deflection curve, and from that we can observe the site conditions, and also we can find out the shear strength. Now this is the basics behind axial strain, axial stress, and axial compressive stress, as well as the corrected area. Now the student can measure the change in length, and original length was about 76 millimeters, was said to be initial length, and from this you can find out what is the axial strain. Axial strain is the del L by L0, and if you want the corrected area, you have A is equal to A0 by 1 minus epsilon. So this epsilon is the strain, axial strain, and A0 is the initial cross-sectional area derived from 38 millimeter diameter, and the compressive stress is nothing but sigma is equal to P by A. Now, this is defining the failure. You can see that the 15% strain corresponds to the load of failure, or otherwise directly obtained from the peak of this curve, which was plotted by the software, or you can plot it manually if you are doing the experiment manually. Now, this was the graph obtained finally by the students after the experiment. You can see that in this we have this as peak value, and the corresponding peak value was about 4.7 to 4.8 kg, and the corresponding penetration was found to be 2.7 or 2.5 mm. So around 2.5 to 2.7 mm it was observed. And you can see that the load was mentioned in kilograms and the penetration was mentioned in millimeters. Now, this is the undrained shear strength, that is equal to SU, that is QU by 2. What is QU? QU is the compressive strength for undisturbed sample, and QU remolded, if you do the experiment for a remolded state, that is said to be QU remolded, and the ratio between these two is defined as sensitivity of the soil. Now, this is the situation after heavy construction, for example, dams, foundation. The pore water inside the soil is not having enough time to dissipate. Because of this, a condition called undrained condition is obtained, where the angle of internal friction is 0. Because pi is equal to 0, the undrained shear strength entirely depends upon the soil cohesion. So what do you mean by cohesion? It is the attraction between the soil particles, and they come closer when you start applying the load and the pore water starts escaping. So that is said to be soil cohesion. And this shearing strength is equal to cohesion, which is equal to compressive strength divided by 2, as mentioned here. So you can see that it is mentioned here. The short-term lap test perfectly mimics the short-term field risk. So this field condition is what resembles the condition in the lab. The lab test particularly is a replica of the site condition, and based upon the lab test we can design the foundation. Now, these three diagrams will give you an idea what is the undrained condition, what is the dissipation state, and what is the steady state. And during the undrained state, what happens is the soil is having water molecules, and these water molecules will start bearing the load. So in this condition, the governing equation is the shearing stress is equal to cohesion between the soil. And as time goes on, the soil particles come closer. So this figure, you can see that the soil particles come closer and the water starts oozing out, or it is escaping like this. So this state is said to be transition state, where the dissipation of the pore water is observed. And the final one is the steady state, which exists for a long time. At this state, all the particles are fully packed with each other, and between the particles you can find out a few water molecules, and at this condition the soil starts bearing the load for a long time, and this condition is said to be steady state condition, and this is governed by Coulomb's equation. S is equal to C dash plus sigma dash tan pi dash, where S is nothing but the shearing strength, and C dash is the cohesion, and sigma dash is the normal stress, and pi dash is nothing but the angle of internal friction. So this is the Coulomb's law, which governs the soil long-term steady state. Now you can see that these are the testing standards and protocol constraints as per IS 2720 or 1973. So thanks a lot for watching. If you have any doubts, you please mention in the comment section. Thank you.